the third session about the harmonic oscillator model. You should be watching this. Well, the first time you should watch it, you probably should watch it more than once. The first time you watch it, you probably should be in Chapter 2, reading Section 2.2, 2.3. And then I guess I would recommend watching it again. You're not going to understand everything that I talk about here if you're just in Chapter 2 initially, though it wouldn't hurt to keep watching it anyway. I would recommend watching it again when you get to Chapter 3, as you work through Chapter 3, and especially when you get to Section 3.6. So I'm going to be kind of covering material from two chapters, Chapter 2 and Chapter 3, in this video. The harmonic oscillator model is one that I've done 2 videos on so far. The thing that's going to be new here, as far as the model goes, is that I'm going to call it the damped harmonic oscillator now, because we're going to try to model the effect of damping forces, frictional forces, on the harmonic oscillator. So here's our picture again. We've got a wall over here. We've got ice down here. But now maybe this ice isn't so slippery. We've got a spring attached to the wall. The wall is immovable, and we've got a block of wood sitting there attached to the other end of the spring, sitting on top of the ice. Because it's going horizontally, we can ignore the force of gravity and just focus on Hooke's law and the differential equation that models the situation. First of all, you have ma, mass times acceleration, equaling the force that you get from Hooke's law, which is in the opposite direction of y, which is our horizontal position, starting from y equals 0 is where the mass is at rest. Some constant k will give you a constant of proportionality, negative k, between this mass times the acceleration and the position y. What if we add damping? Either because the ice is kind of, well, not so slippery, or because there's internal friction from the spring, or because there's air friction, or most likely all 3 of those things are coming in to damp this harmonic oscillator. How do we model that? This is a lot less precise than Hooke's law, and we want to take the point of view that we want to keep things as simple as possible and hope that it works pretty well. How can we keep things as simple as possible? Well, it doesn't really make sense to think of the damping forces as related to the position of the block. If I hold it out here, the damping forces are no greater or less than if it's sitting there at rest. So it's not related to position. It seems reasonable to assume the damping is related to the speed or the velocity. And I guess if we're talking about velocity, it should point in the opposite direction as the sign of the velocity. So if the velocity is positive, meaning the block of wood is moving to the right, then the damping force should be to the left. It should be trying to slow it down when it's going this direction. And if the velocity is negative, meaning the mass is moving to the left, then we want the damping to be positive, to point in the positive direction. So we'd want another negative sign in here, and maybe some constant, I'll call it b, times, oh, mistake there, times v, where v is dy dt. V is the velocity, the derivative of y with respect to t. So we made our differential equation more complicated, but perhaps more accurate. This is more typically written in another way. Get 0 on the right side and everything else on the left side, and we can write it like this. And for sake of convenience, it's nice to deal with leading coefficients that are 1. So if I divide everything by m, That'll get a leading coefficient of 1. If I call B over M P and K over M Q, then my equation looks like this. So P is B divided by M, and Q is K divided by M. So there's my second order simplified differential equation, and it's linear. We'll see that linear combinations of solutions will still give you solutions. Modeling a harmonic oscillator with damping. This kind of model is important not just because masses on springs are so important, but also because it comes up in other areas. You'll see harmonic oscillators come up in other areas if you do lots of physical modeling. So it's something that's worthwhile to study and understand. How do we solve it? Well, if we're thinking back toward the beginning of Chapter 2, well, even into Section 2.3, we can try to solve it by guessing. What should we guess? In the first two videos about the harmonic oscillator, we guessed cosine and sine. We didn't have a damping term, and those turned out to be good guesses. In this case, it's not so clear what to guess because we have this damping. What function should I guess whose second derivative plus a constant times its first derivative plus another constant times the function will give me 0 no matter what t is? It's not so clear. One big theme that you should get out of this course is when you have linear equations, be they first order or second order or even third order, and you really don't have much idea what to guess intuitively, guessing an exponential function, believe it or not, is usually the best way to go. When I write this, y equals e to the s times t, s is an unknown. S is an undetermined coefficient, you might say. I'd like to know what value of s, if any, will make this function a solution to that equation. So we just try it. See if there seems to be any value of s that will make this function a solution. Let's find its derivative. By the chain rule, I need an extra factor of s in front. I need its second derivative, giving me another factor of s in front. Is that blue coming out okay? Okay. Now plug these into the differential equation on the left-hand side and see if you can find a value of s that will make the left-hand side identically equal to 0 no matter what t is. Y double prime plus py prime plus qy, the left-hand side, for this kind of guess, is going to give me s squared e to the st for y double prime, plus ps e to the st for p times y prime, plus q e to the st for q times y. We want this to always equal 0. When you're trying to solve an equation where you're setting something equal to 0, it's usually a good idea to try to factor it as much as possible. And the same thing happens here. It's a good idea to factor this as much as possible. In particular, we can factor out the e to the st. To get that. I want this to always equal 0 for all t. Is there a value of s that will make that equal to 0 no matter what t is? Well, the first thing to realize here is the e to the st is irrelevant. e to a power is never ever 0. Some of you have heard a story about a grad school professor I had who, well, I made a mistake on one of my exams and I wrote e to the 0 equals 0. Oh, never ever do that. He appropriately chastised me by grading my exam and writing in big letters, "What were you thinking? Were you sleeping? Are you crazy?" Okay? That's kind of the way he talked. He was one of my favorite professors at the University of Minnesota. And, well, I didn't care for his chastisement at that moment, but I realized I must have been sleeping. That was a bad thing for me to do. E to a power is never 0. Well, some engineers might say e to the negative infinity is 0, but, well, forget that I ever said that. E to a power is never ever 0. So the only way for this equation to always equal 0 is if the other factor equals 0. And that's a quadratic equation in the unknown s. Just use the quadratic formula. And as I start to use the quadratic formula here, an amazing thing starts to form in my mind, an amazing realization. E to the st must be a good guess. Exponential functions are good guesses for equations like this. Evidently, I haven't really proven it yet, but if I know P and Q and I plug it into this stuff and find S, I'm going to get solutions. And moreover, because I have two distinct values of S, at least if this thing inside the square root is non-zero, I'll get two solutions that are not multiples. They'll be linearly independent, and a linear combination of those two for this second order equation will be my general solution. Let's go ahead and consider some particular numbers for P and Q. Let's pretend our original equation looks like this. Y double prime plus 5y prime plus 6y equals 0. Meaning P is 5 and Q is 6. That's ultimately going to give me values of S, negative 5 plus or minus square root of 25 minus 4 times 6 is 24 over 2. Negative 5 plus or minus 1 over 2. Negative 5 plus 1 over 2 is going to be negative 2. And negative 5 minus 1 over 2 is going to be negative 3. Evidently, these two values of S will make e to the st a solution. I also could have factored this equation in this case. I wouldn't necessarily need to use the quadratic formula. In fact, you can just jump from this differential equation to this equation, this quadratic equation involving S. Sometimes that quadratic equation has got different names. It's related to the original differential equation. Sometimes people call it the auxiliary equation. I also have heard the name indicial equation. And I might sometimes call it the associated quadratic equation. Its roots give you the values of S that will make e to the st a solution. And so the general solution in this case, as a scalar, is an arbitrary constant k1 times e to the negative 2t plus an arbitrary constant k2 times e to the negative 3t. You should take a few minutes to check that e to the negative 2t and e to the negative 3t definitely work by actual substitution. Find their first and second derivatives and plug them into the left-hand side here and see that everything cancels to give you 0 at the end. You should stop this video right now and do that for a few minutes to check this. They're not multiples of each other, and so this will be the general solution, which of course we can use to find solutions to initial value problems. Let's go ahead and write down a particular initial value problem. Say y of 0 is 1 and y prime of 0 is 0. So I'm stretching it by a meter and letting it go from rest. This thing is going to give me the equation k1 plus k2 equals 1 just by plugging in 0, e to the 0 is 1. And if I find the derivative of this, I get negative 2k1 e to the negative 2t minus 3k2 e to the negative 3t. And if I plug 0 in for t in that, I'll get the algebraic equation negative 2k1 minus 3k2 equals 0. Solve the system for k1 and k2. Let's see, if I multiply this equation by 2 and add it to this one, the k1s will go away, and I'll be left with, let's see, a 2k2 minus 3k2 is a negative k2 equals 2 plus 0. So it looks like k2 is negative 2, and that would mean k1 would have to be 3. Double check that. My head here. Yeah, that's going to work. And so my particular solution would be 3 e to the negative 2t minus 2 e to the negative 3t. That would solve the initial value problem where I've got these two initial conditions. If you think about this, and think back to what you saw in the first two videos about the harmonic oscillator, this may seem a little strange. I mean, don't masses on springs oscillate? You think about what the graph of this looks like, and in particular, if you get your calculator out and plug it in and graph it, you'll see that it doesn't oscillate. What's going on there? Well, basically, in this case, the damping is so great relative to the spring constant that we don't get any oscillation. There's so much friction that it doesn't oscillate. Maybe it's sitting in a tub of water or molasses or something. There's so much friction that it doesn't oscillate. This can happen with these kinds of differential equations. You don't necessarily get oscillatory solutions. If you're reading chapter 3 right now, there is a corresponding system, and you even encounter this in chapter 2, a corresponding system for this differential equation. And you want to be free to think of these things in both ways. One equation for the system is that y prime equals v, the derivative of position with velocity. The second equation for the system is that the derivative of velocity, the acceleration, is, well, what would it be in this case? Okay, I guess I'm assuming, if I'm really thinking of these as being position and acceleration, or position and velocity, y and v, I guess I'm taking the mass to be 1 in a sense. Well, I guess not. I guess it's just that the coefficients are still what I had before, b over m and k over m. What's going to happen, I compare this equation with this. V prime is y double prime. If I solve this equation for y double prime, I get negative 5y prime minus 6y. I'm going to put the y first. Minus 6y minus 5v. If I'm writing it this way, I should put the y first and the v second, because now that's going to make sure, it's going to guarantee that my matrix is correct when I write this in matrix form. Introducing the vector capital Y to be little y, little v, and a matrix A whose entries are the coefficients 0, 1, negative 6, and negative 5 for the right-hand sides here. The system in vector matrix form is dy dt equals a times y. Let's see what happens when we find the eigenvalues of A. The trace of A is the sum of the elements on the diagonal. That's negative 5. The determinant is 0 minus negative 6. That's positive 6. I'm just multiplying the main diagonal elements and then subtracting the product of the off-diagonal elements. The eigenvalues, which we call lambda, is the trace plus or minus the square root of the trace squared minus 4 times the determinant over 2. -5 plus or minus square root of 25 minus 4d. And lo and behold, if you think back to what happened a few minutes ago, these eigenvalues are the exact same things we got before. -2 and -3 for the roots of that other equation. In fact, that other equation really was the same thing as the characteristic polynomial that you read about and learned about in chapter 3, or will do so when you get there. What about the eigenvectors? If you're only in chapter 2, hang on. I will come back to stuff you are familiar with. Lambda equals -2. I go back up to A, and I'm thinking about the equation A minus lambda times the identity matrix times a vector equaling the 0 vector, and thinking about that equation in scalar form, and also if I plug in an eigenvalue, I'm going to get a redundant system. I've got to subtract lambda from the diagonal elements. 0 minus -2 is going to be +2, and that's the coefficient of x in this equation when I write it in scalar form. The 1 up here stays the same. The right-hand side is a 0. Now for the second equation, the -6 stays the same. It's off diagonal. I take the -5 and I subtract -2. -5 minus -2 is going to be -3. These equations are redundant. You get from this one to this one by multiplying by -3. So I can take either one of them to help me find an eigenvector. If I set x to be 1, y will be -2. And that'll be my eigenvector for the eigenvalue -2. What about the other eigenvalue of -3? Do the same kind of thing. 0 minus -3 is +3, plus 1 times y. Then -6x. -5 minus -3 is -2. And once again, we get a redundant system. Solve either one for y in terms of x or vice versa. And that gives us an eigenvector of 1, -3. So in vector form, we can write the general solution to the corresponding system as a linear combination of e to the lambda t times the corresponding eigenvector for each one of those values of lambda. K1 e to the -2t times 1, -2 plus K2 e to the -3t times 1, -3. And that would be the general solution of the system. And these things are related, as you might hope. I mean, even when you're in chapter 2, you do start to study systems. These things are related. If I go back to my general solution of the original second order equation, not the first order system, but the second order scalar equation, one scalar equation, it looked like this. Its derivative, little y prime, or you might call that v, looks like this. Now imagine putting these things in a vector. Maybe I'll even do it like this. And compare. Look at the relationship between this vector and this vector. They're the same. If you break this vector apart into pieces, you'll get this, or vice versa. If you add these two things, you'll get this. You first need to multiply this scalar, k1 e to the -2t times this vector, and this scalar, k2 e to the -3t times this vector, to get two vectors without scalars in front. Add those two vectors, you're going to get this. They are very much related to each other. And what this is illustrating then is if you've got a second order equation like this that I started out with, like that, it's easier, I think, a little bit at least, to get to the general solution even in vector form by first finding the general solution in scalar form, then differentiating that function to get the velocity, and then putting those in vector form and breaking it up into a linear combination like this if you so desire. So you don't have to think about finding eigenvectors, which I know can be kind of a pain sometimes. So I think this method is a tiny bit faster, and it's probably worth your while. Well, I'm running low on time with what I wanted on this video. I was hoping to maybe do another example. I think what I'll do is I will write down that other example that I was hoping to do, but we won't completely analyze it. Y double prime plus 4y prime plus 20y equals 0 was the other equation that I wanted to look at. The corresponding system, by the way, would be y prime equals v, v prime equals negative 20y minus 4v. And so the matrix capital A would be 0, 1, negative 20, negative 4. But rather than actually trying to solve this system, which I guess I will have to leave for the next harmonic oscillator video, let's see if we can just look at the computer and see what it looks like, so we can predict what's going to happen on the next video. I know on the harmonic oscillator video 2, the computer screen didn't work out real well, but it's looking okay. Hopefully this is looking okay. We'll go to mass on a spring. Well, let's see, maybe that's not the best place to go because the sliders don't go as far as we would want them to if we set m to be 1. K can only go up to 2 and B can only go up to 4. Oh, I made a mess for myself here. Bear with me while I set my display back to something bigger, smaller. Where did it go? Let's try that again. I think what I'm going to do instead is go to HBG System Solver. And let's just see what happens here. Okay, so y prime is v, that's the first equation. In HBG System Solver, x is going to be playing the role of y, and y will be playing the role of v, and so actually this first equation is okay. I don't have to change it. dx dt equals y is going to be the same as dy dt equals v on the screen. The second equation is dv dt equals negative 20y minus 4v, so I really want a negative 20x minus 4y for the second equation. Negative 20 times x minus 4 times v minus 4 times y. Here's the vector field, which you learned about in the second harmonic oscillator video, although this will actually be a direction field. Let's see if we can kind of tell what's happening here. I'll just pick an initial condition. It does oscillate a bit. It looks like it's not oscillating much. In fact, the model is oscillating infinitely often. This isn't really illustrating it as well as I was hoping. Let's see if we made the damping even smaller, if we made this, the damping is in front of the velocity, which for this thing is the y. I made that even smaller, like 1. It makes the eigenvalues and eigenvectors not so simple, probably, but maybe we'll see the oscillation more. There we go. And it really is oscillating in the model infinitely often, even when we use a 4 for the for b over m. But this illustrates it more. And so what we should expect when I solve this on the next video is we should expect cosines and sines to come back into play. But how is that going to happen? Well, if you're in Chapter 3 right now, you probably already know. If you're in Chapter 2, I guess I'll give you a little hint. Complex numbers are going to be what essentially is going to end up combining exponential decay with trig functions. A complex exponential, e to the st, where s is a complex number, a plus b times I, where I is the imaginary unit, the square root of -1, will end up being a complex valued solution, and a remarkable formula called Eulers Formula will allow us to translate that complex solution into some kind of combination of exponentials and trig functions. So that's what you have to look forward to in the next video.